Greetings, ladies and gentlemen. I'm honored to have this opportunity to present the paper MadDroid, Characterizing and Detecting Devious Ad Contents for Android Apps. My name is Tianming Liu. I'm currently a master candidate at Beijing University of Posts and Telecommunications. The mobile app ecosystem has seen rapid growth in the past few years. Stats from MadDroid shows that the number of apps in Google Play has reached 2.8 billion this year, and this number is continuing growing. In the meantime, more than 95% of these apps are free. Recent study also revealed the trend that more and more paid apps have been released as free ones by their developers. Actually, developers of these free apps are monetizing through in-app advertisements to collect revenues from ad networks. There are more than 100 certified ad networks on MadDroid, and many more newly emerged ones. Ad networks distribute mobile advertisements through the ad libraries they provide for developers to embed in their apps. These ad libraries are widely used. Take AdMob for example. Over half of apps on Google Play are embedded with AdMob library. Mobile advertisement has been rapidly growing in the past couple of years, and it is now a huge industry. In 2019 alone, the revenue of mobile advertising reached $190 billion, and it is expected to surpass 280 by 2022. It goes without saying that advertisement drives the economy of the app ecosystem. However, recent news and reports have shown that the content in mobile ads poses a number of threats. For instance, in 2018, researchers found more than 60 apps on Google Play displaying porn ads to kids. A recent report also reveals that some ad contents actually come with coin miner scripts, which uses the resource of mobile devices to mine digital currency, Monero. Apart from the security risks introduced by ad content. Here's another interesting example. When using mobile apps, it's not uncommon to see interstitial ads like this. The normal reaction is to click on the cross symbol to close the ad. Naturally, we would think the cross is a close button, but when clicking on the cross in this particular ad, instead of being closed, it instantly starts the download of another app. At first, one may think it's mistakenly touched, but after several failed attempts, we discover that clicking on the cross is no different than clicking on anywhere else of these ads, which means the cross is useless. Upon further investigation, we discover that the cross symbol is actually embedded in this image, tricking users to click on the ad. We call this type of fraudulent behavior click deceptive. These threats introduced by mobile ad content are putting the security and privacy of users at risk, which in turn jeopardize the whole app ecosystem and need to be detected and mitigated immediately. But before I start on the detection of these threats, let me briefly describe the general working process of mobile ads. When an app starts running, the presented user interface is called a home page. After the ad library within the app corresponds with the server of ad network, such as downloading ad images, JavaScripts, HTML files, an ad view is successfully loaded on the home page. Once this ad view is clicked, the ad library will then correspond with a content server. There are three types of ad content that are recurrently pushed to users after click. The first is a redirection link that switches the current homepage to a landing page for displaying further ad information, such as an online shopping page where the user can purchase the items that were advertised within the ad view. The second is a deep link to Google Play for users to install the advertised apps. The third is the automatic download of APK files. After the downloading is completed, an app installation page would pop up, and the users can decide whether to install the downloaded app. Therefore, based on different phases of ad, there are two types of ad content: ad loading content and ad clicking content. Unfortunately, both types of ad content may be comprised of artifacts that may threaten the security and privacy of users. We refer to such ad content as devious, since they are deceitful for all parties, including app users, developers, and potentially ad networks, who are unaware of the situation. While a few research have focused on the deviousness of ad clicking content, there has been no study on ad loading content. Through a thorough investigations on the developer policies of popular app markets such as Google Play and Huawei, some media reports, and real-world apps, we make the following categorizations of devious ad content, which comprises 5 groups. The first group is click-deceptive image. Normally, the close button of an ad is a separate image, which allows ad networks or developers to set a close event on the ad, while a click-deceptive image is an ad image directly embedded with a cross symbol, tricking users to click on the ad. The second group is censored image, which refers to ad images that fall under censorship according to state legislation or the market policy. We enumerate 4 cases here: gambling, violent, medical, and pornographic images. The third group is malicious scripts. Mobile apps are often displayed with the web view widgets in Android, which can legitimately run code to interact with the host app. Unfortunately, malicious scripts may also be injected in the ad and jeopardize the security of mobile devices, such as coin miner scripts. The first 3 groups fall into the category of ad loading content, while the last 2 are ad clicking content. Some mobile ads, after clicked, may jump to landing pages with malicious content. These links are called malicious redirection links. Some ads, when clicked, may also directly start the downloading of malicious apps. After a categorization of devious ad content, we seek to propose an effective approach to automatically detect these types of devious ad content in Android apps. There are mainly 3 challenges that need to be addressed. The first is how to automatically trigger and collect ad content. In order to collect both types of ad content, not only do we need to trigger the appearance of mobile ads, we also need to click them. Unfortunately, mobile ads could be delivered in different sizes, different widgets, different numbers and places. We need a sophisticated exploration approach to effectively traverse the ads within apps. The second is, mobile ad contents can be extracted from the network traffic which are related to ads. However, while collecting ad traffic at runtime, non-ad traffic and ad traffic are inevitably mixed together. We need an effective approach to separate them apart. The third is how to differentiate devious ad content. For each group of devious content, we need an effective approach to detect them. In order to address these challenges, we propose MadDroid detection framework, comprised of 3 modules to deal with the 3 challenges respectively. The first is TCM, which focuses on automatically triggering and clicking mobile ads to generate and collect all traffic at runtime. The second is CEM, to harvest both ad loading content and ad clicking content from general traffic. And the last, DDM, to identify the deviousness of the extracted ad content. In the following slides, I will introduce each module respectively. The first is TCM, Traffic Collection Module. The goal of this module is to trigger and harvest all network traffic involved in advertising with automated app testing technique. However, traditional automated testing approaches, such as Monkey, generate random test cases that are not ad specific, causing the majority of dynamic execution wasted on exploring irrelevant UI states. A study also reveals that 90% of the UI states are not ad involved. Therefore, we propose an ad-first exploration strategy that are customized for the loading and clicking of ads. According to a previous study, most ads are loaded and displayed in the main and exit UI pages of an app. Therefore, our ad-first exploration prioritizes the views of these pages with a breadth-first search algorithm. During the exploration, whenever an ad is loaded, we immediately click on the ad, which is identified through view tree. From view tree, we can obtain the basic view information of a given UI state, such as position, size, and class name. Based on a recent work, ad view is implemented by the widget of web view, image view, or view flipper. Therefore, to ensure good coverage, our ad-first exploration prioritizes and click on each view that falls in any of these 3 classes. During the exploration, all traffic are recorded. including ad traffic and non-ad traffic, such as parallel traffic from core ad functionality. Therefore, we need CEM, Content Extraction Module, to identify ad-related traffic from all network traffic and then extract ad content. Here's a simplified list of HTTP requests harvested during the exploration of an app, where the highlighted domain is a known ad domain of a famous ad network, startup. Given a wide list of ad domain, it would be easy to pick out ad load traffic from a collection of network traffic. Unfortunately, it is impossible to manually build a wide list containing all ad domains, for mainly two reasons. First, there are a plethora of ad libraries. AppBrain currently holds 140 certified ad networks. There are more uncertified ones that we are not familiar with, and ad networks from different countries and regions, not to mention newly emerged ones. Secondly, we empirically discovered that one ad library may correspond with multiple domain names. For instance, we found this Chinese ad network has dozens of ad domains. This phenomenon makes it harder to manually collect a complete wide list of ad domain. To address this issue, we propose a runtime HTTP hooking approach to iteratively identify ad domains so as to locate ad load traffic. It works in 3 steps. First, we dynamically hook all the network APIs on the framework level to monitor HTTP requests within the app. Then, we trace the call stack of the network APIs to locate the package in apps that initiated this HTTP request. Therefore, we create a map between package and domain. If a package belongs to a known ad library, all the domain triggered by this package will be regarded as ad domain. Similarly, if a domain is a known ad domain, the corresponding package will be flagged as ad library. Therefore, we can build a wide list of ad domains iteratively, and then use it to locate all ad load traffic. Here's an example of how CEM works. This app is requesting for an ad with this HTTP request. Our hooking approach captures this network behavior, and the API OKHTTP client is called. Then we dump the call stack of this API and find out the package that initiated this HTTP request belongs to an ad library startup. Therefore, we obtain a map between ad library and ad domain, which can be used to iteratively identify ad domains and then locate ad load traffic easily. Then, let's take another look at the response of this ad load request. The response is in HTML format. In its response body, we can find this particular URL, which is the start of the ad click traffic of this ad. From this URL, after a chain of redirection links, the ad click traffic reached its landing page. By analyzing the response content of ad load traffic, we can successfully locate the ad click traffic of this loaded ad. Hence, both ad load traffic and ad click traffic is identified from general network traffic. Then, from the response body of the marked ad traffic, we can easily extract ad content, including ad loading content, such as images and executable scripts, and ad clicking content, such as redirection links, the promoted apps through Google Play, and the directly downloaded APK files of advertised apps. The last module of MadDroid is DDM, Deviousness Detection Module, which contains 3 plugs. The first is to detect click-deceptive images. As previously mentioned, the main characteristic of click-deceptive images is the embedded cross symbol on ad load images. Therefore, we apply the algorithm of object recognition to detect the embedded cross. There are many sophisticated algorithms in object recognition. We choose to adopt YOLO, you only look once, which is proven to have achieved higher efficiency and accuracy. But there are no work related to the detection of cross symbol. Therefore, we build a training set and testing set from scratch. Although we have already harvested some samples of click-deceptive images during our manual investigations, the obtained set is not representative and not nearly enough for training. But we did harvest more than 2,000 normal ad images that are not embedded with cross, and over 100 separate images of cross symbol. Therefore, we randomly embedded this separate cross on normal ad images and formed a training set of more than 2,000 embedded images, while the testing set is comprised of 200 original images and the embedded version of them. With only 5 false positive and 4 false negative, YOLO achieved more than 97% on both precision and recall at detecting cross. The second plug is to detect censored images. Google Vision API is applied in this plug, which has been widely used and proven to be effective in flagging censored images with its safe search feature. Given an image and a censored type, this API will yield a level of 1 to 5, 1 being very unlikely, 5 being very likely. We count an image as censored if a 4 or higher is given on a certain type. But Google Vision API does not support the detection of gambling ad images. Because of the heterogeneity in gambling, it is hard to build a graphical model that captures the gambling instance accurately. Therefore, we resort to a simple approach that focuses on the text embedded in the ad images. We first rely on OCR to extract any text from a given ad image, and then perform a keyword matching on this text to see if it's gambling related. The keyword list comes from the top searched gambling keywords in Google and frequently presented words on gambling websites in different languages. The third plug deals with all non-image malicious content, including malicious scripts in ad loading content, and malicious apps, malicious redirection links in ad clicking content. We rely on VirusTotal to detect them, which integrates over 60 antivirus engines and is widely adopted by the research community. Then, to evaluate the effectiveness of MadDroid on detecting devious ad content, we performed a large-scale experiment. The following slides will first introduce the dataset we used and the experimental setup, and then summarize the overall results of the detection, after which we will focus on 3 noteworthy issues reflected by the result of our experiment: the distributed malware in ad content, the host apps of this devious content, and the role of ad networks. For the dataset, we resort to the well-known Andrew Zhu. Since we are only interested in apps with advertisement, we further leverage VirusTotal to collect adware. We consider a given app is adware as long as one antivirus engine flags it as such. To this end, we randomly collect 40,000 adware from Andrew Zhu, including both Google Play apps and apps from third-party markets. The experiment is performed on 6 Nexus 5 smartphones. Considering that loading an ad from a remote server may take time, we set the transition time between simulated actions to 5 seconds. Overall, the automated exploration for each app takes on average 2 minutes. Contrary to prior related work, we use real devices instead of emulators, given that ad libraries may implement verifications to avoid serving ads on emulated environments. In total, we collect over 2.4 million HTTP messages. Over 20% of them are ad load traffic. Over 27% are ad click traffic, from which we harvest 80,000 ad images, 50,000 scripts in ad loading content, and ad clicking content, including 50,000 redirection links, 2,500 directly downloaded APK files, and another 2,000 apps promoted through Google Play. Of this harvested ad content, the stats of our deviousness detection is shown in this table, from which we can see the devious rate of ad loading content is less than 1%, while the rate of ad clicking content is much higher, which indicates that ad clicking content are more likely to be devious. But still, we cannot overlook the deviousness of ad loading content. While ad clicking contents will only be triggered upon being clicked, ad loading content will in any case be delivered to users. Totally, 800 ad images are considered devious, specifically 500 click deceptive, 170 pornographic, 60 medical, 37 gambling, and 9 violent ad images are detected. Then we take a look at the malware distributed by ad content. 57% of the downloaded APK is flagged positive by VirusTotal. More than 30% of those are even flagged by over 10 antivirus engines, indicating a consensus on their maliciousness. We further searched their package names on Google Play and the ASO website, and discovered that over 90% of them are not on Google Play, and over 20% are not on any markets, which suggests ad content is a covered channel to distribute malicious apps. Efforts should be made to mitigate this issue and to maintain the security of users. Of the 40,000 apps in our dataset, 6% of them are detected to have delivered devious ad content. The fact that more devious content are collected than the number of host apps suggests that one app may repeatedly present devious ad content. And even popular apps could contain devious content. For example, this gaming app called Magic Candy is detected to have provided click-deceptive images. It is now still available on Google Play and has received more than 10 million installs. One of the most liked comments is also complaining about the ads that can be skipped. This is evidence that the identification and blocking of devious ad content remains an unresolved issue in this industry. App markets need to apply effective approaches such as MadDroid to inspect the ad content of their apps and protect our mobile ecosystem. With our hooking approach in CEM, we have identified more than 3,500 ad domains in our experiment. It's interesting to see that, for devious content such as malicious apps and click-deceptive images, most of them comes from ad networks that is lesser known, while for other types of devious content, many comes from popular ad networks. For instance, over 46% of malicious links are distributed by Startup and Google AdMob. Considering their popularity, many users may have already been affected by this devious content. We argue that ad networks need to be more responsible for such threats and implement adequate means to keep devious ad content from users. The HTTP hooking approach in CEM is essential to locating and extracting ad content. Therefore, we evaluate its effectiveness on identifying ad domains. Recall that the hooking approach takes as input a set of ad libraries or ad hosts to build the mapping iteratively. We evaluate our approach through three settings. Setting 1. Input ad libraries only. Specifically, we use the 52 popular ad libraries from library detection tool LibRadar. Setting 2. Input ad hosts only. An ad domain list of 1,300 hosts applied in a similar study was chosen in this setting. And setting 3. Input both together. This figure here illustrates the experimental results, where x-axis represent the number of ad libraries and y-axis represent ad hosts. It's interesting to see that no matter starting from which setting, they all tend to converge to the same result within 15 iterations. Compared to using the list of ad hosts in setting 2 alone, the number of ad hosts has almost tripled, which in turn immensely increased the collection of ad contents by 126%. During this evaluation, we made some interesting discovery that one ad library can trigger multiple ad hosts, and one ad host can be triggered by multiple libraries. The top 5 involved libraries and hosts are shown in this figure. For example, DoubleClick, the domain of Google Ads, is even triggered by 175 ad libraries. From our further investigation, we discovered that some top-ranked libraries are usually embedded with multiple other ad networks, which are further used to trigger ad requests. This is called ad mediation. Our analysis also reveals that some libraries pointing to the same ad hosts are actually the obfuscated ones of the same library. Take AirPush for example, a famous ad network. We find various ad libraries with different package names but similar format, which are all the obfuscated version of the AirPush library. This finding suggests that our hooking approach can even be a promising method to identify obfuscated libraries. In conclusion, our study proposed a novel ad traffic identification approach which increases the collection of ad content by 126%. We devise and implement MadDroid, a detection framework that focuses on the deviousness of both ad loading content and ad clicking content. And here are some takeaway messages. Devious ad content is indeed a serious issue in the Android ecosystem. 6% of apps in our dataset is detected with devious ad content. App markets and advertisers should take efforts to mitigate and prevent this issue. We have released our dataset and results at GitHub for future reference. Thank you for listening. Any kind of collaboration is welcome. Feel free to contact me or my advisor Haoyu Wang at Beijing University of Post and Telecommunications. Here's our contact information.